let's look at an example using the individual potential energy values between two particles in a typical problem. Now, since, as it says here, since work equals negative the change in potential energy, these types of problems where we have multiple point particles and we're looking at the potential energy of this system of particles will often be worded as calculate the work required to assemble or to set up the particles into these positions. The only other version of this type of problem is the work required to disassemble or pull them apart to infinity. So in the figure we are looking at here, we have three particles. We have a particle 1, which I'm labeling with my orange color, a particle 2 with my purple, and a particle 3 with the light green. And what we are being asked to calculate is how much energy was required to bring this purple particle 2, that 5q in from infinity. So the 5q, the purple particle, started out here at infinity and was brought inward to its final position, and how much work was required to get it to that position. Well, what we are going to calculate is the change in potential energy. We are then going to put the negative out front, and that is the work done by the field. And then we have to see whether the question is asking us for the work done by the field as it was assembled or the work done by an external force as it was assembled. And those answers will simply be the opposite of each other. Well, let's calculate the work done by the field. So I will always calculate the work done by the field because that matches my equation, W equals negative delta U. So calculate the work done by the field and then see how your answer would change if it's asking you for the work done by the external force in that process. Well, we definitely are going to be utilizing our equation. U, the potential energy value in joules between two particles, Q1 and Q2 in general, is given by K, Q1, Q2 on R, and we put the plus or the minus in for the Qs. Well, it's a delta U that we're interested in. Now, in this problem, they are telling us that both initially and finally, particle 1 is at this position, and particle 3, both initially and finally, is at this position. So in both cases, they are a distance r apart. So 1 and 3, right, will initially be at a distance r, and 1 and 3 will finally be at a distance r. So we'll see that when we take the delta U, there's no change in potential energy because the equation, right, the U equals K, Q1, Q2 on R remains the same initially and finally. So we're going to end up losing those terms. Well, how about the potential energy values between 1 and 2 and 2 and 3? Well, 1 and 2 start out with a distance r of infinity apart. 2 and 3 start out with a distance r infinity apart. So that's what we're showing here. And then finally, 1 and 2 are a distance 2d apart. And 2 and 3 are a distance d apart. So basically, we need to calculate the joule value, if we were given actual numbers to plug in, for each of those positions, and then take the delta U. Well, if we leave it in terms of the variables, what we get is the U final for 1 and 2 is the UD. So that's the 2D that we have here. The 2 and 3 are at a final position of D. We've already seen that the initial and final for 1 and 3 are going to give us the same values. So when we do our subtraction, they will give us 0 when we subtract. Now, since we have little r equals infinity, notice we lose the initial potential energy joule value for particle 2 when it's out here at infinity, because that distance, right, that's infinity, and that distance is infinity. Now, when we plug in our numbers, we get a somewhat interesting result here, somewhat fortuitous result, that when we take the delta U, we end up getting 0 joules. So how is it possible that it took no energy? In this case, it would be 0 for both the work done by the field or the work done by an external force to bring that 5q particle, particle 2, in from infinity and put it here. Well, if we think about what's going on, and as it says here, that this answer doesn't have to be 0, won't be 0 in most cases, but in this case, what it's telling us is that positive 4q is pushing back against the positive 5q as we bring it in from infinity, right? It's pushing against it. Whereas the negative 2q is trying to pull it in. So you have competing effects. And then once we get past our dashed R line here, the positive actually is going to try to push it into place, and the negative will try to pull it out. And all of that pushing and pulling is going to end up doing the same amount of work, the same amount of energy as we bring it in from infinity. So a lot going on here in terms of the technicality of making the calculations and seeing what's going on. We'll be doing more of these point particle systems as examples, so you will get a better feel for how they work. So please pause the video here, make your annotations, and we can, of course, talk more about this.